find that silly. But we are getting into, this was I think chapter 7 in Algebra 2 last year, graphing polynomial functions, solving polynomial functions, the zeros, telling how a function ends, and really I was talking in second hour today, like my why a lot of times is, well, because you need this for calculus, and if you're not ever going to take calculus, it kind of stinks that you have to learn it. But, you know, that's why this class is called Precalculus, because it's to get you ready for calculus, but then lots of people don't take calculus. So many times the NY will say, you'll need this if you study calculus, and most people just get annoyed by that answer, but that's all I got. Sorry. But let's jump in here. Let's talk about polynomial functions. So here's something that maybe you've never thought about, but it's kind of a cool thing about the graphs. A polynomial function of degree n has at most n minus 1 local extrema. It's a fancy math way. Local extrema are just the max or mins on the graph. And really what we're doing in these last two sections before we take a test is getting able to solve these equations and being able to graph them. So a lot of the stuff I'm giving you today are like helpful things for when we graph, like those x to the 5th equations, things that we don't know what they look like, so these are kind of hints for you. So a function of degree n has at most n minus 1 max or mins, and at most n zeros. So it could have less, but this is like the most that it could have. We just had this discussion in second hour today, because I don't know the answer to that. I've always spelled zeros Z-E-R-O-S, but Cora said that she thinks it's Z-E-R-O-E-S. And I've never in my life spelled zero like that, but who says zeros that often, right? Okay, well, I'll look it up while we, maybe it.
Because I see it both ways and I kind of think.
Right. Man, this is like, these are all people that actually dictionary. I was a little confused by that. The best one that I can think of here is x squared. It's an easy one to think about. If you have the function f of x equals x squared, which we should all know what it looks like, how many max or mins does x squared have? 1, which is 1 less than a degree. It can never have more than 1 term on the x squared function, ever. It's a parabola. And it has at most n zeros, which means the most zeros it can have is 2. Sometimes it has 1, sometimes it has none, but the most it ever has is 2. Right? So that's kind of useful when we're graphing it. So this is the first part of your homework. I'll let you write this down when I try to look up the stuff like zeros. I should just like Google it. It'd be much faster than looking up a dictionary. But. And this says, yeah, ROS or ROES. Both are acceptable. I'll just tell Cora that because Zane was making fun of her for saying that you spelled zero ROES. There are like 13 definitions of zero. How about that? Impressive. The first part of your homework today is supposed to be very similar to what we just did, talking about transformations. But if you'll notice, in the last chapter, what we really focused on were like parabolas and absolute value. But today, I could give you x cubed or maybe x to the 4th. And it says, describe how to transform x cubed into 2 times x minus 3 cubed. And then sketch the graph and give the y-intercept. Well, first of all, it's important to know, what does the graph of x cubed look like? One of those 10 functions we should know. X cubed, what's it look like? Show me with your finger. Oh, look, there we go. All right, good to know. I call it the S-shaped graph. I know it's really not an S, but that's what I think of when I'm graphing it. Right, it kind of goes, this side goes up, this side goes down. I don't know that that's really an S, but that's what I think of. So describe what's happening. What does this minus 3 in the parentheses do to my graph? Right, 3. What does this 2 in front of the graph, do? stretches it by a factor of 2, so we could say vertical stretch factor of 2. How about that for what we're writing? Yeah, so it's going right 3 in a vertical stretch. If you know what the basic graph looks like, it makes graphing this not so hard to do. If you're not sure what's going to happen, XY chart is always an option, but hopefully the transformations help you a little bit, and it's a good little reminder. You don't have to make a lot of points on x cubed because x cubed gets really big and really small very quickly, but you want to at least think about what's happening. So normally x cubed starts here at 0, 0 is how I think of it, and then this side goes up, this side goes down, but I'm moving right 3, so I'm going to go over here, right 3. And then again, just like with parabolas, we can think about what we normally do. So normally for x cubed, if I go over 1, I go up 1. But if I'm stretching it by a factor of 3, what's going to happen when I go over 1? Factor of 2, I mean. Stretching it by a factor of 2. When I go over 1, that means I'm going to go up 2. You with me on that? If I'm stretching it twice as much. If there was a 4 in front of it, I'd go up 4. If there's a 7 in front of it, I'd go up 7. And normally, if I plug in -1 here, I go back 1. But since I'm stretching it, when I go back 1, I'm going to go down 2. But still that S shape is just kind of stretched out a little bit more. I'm fine with picking no other points on here, but make sure you make this graph accurate when you make it. Normally when you plug 2 in here, what do you get? 2 to the third is 8. If I stretch that by a factor of 2, when I go over 2, how much would I go up? Normally I go to 8. I'm stretching by a factor of 2, so I'm going to go up 16. So just think about that when you connect these dots. Here's what I don't want you to do. Don't make this go up and go way out like this. Because if I go over 2, my next y value is going to be way up here at 16. So that's going to go up very quickly. So make sure you make that graph go up and down pretty much almost straight up. Because it's going up to 16 at the next point. Follow me on that? So we're stretching that out. So just be careful when you make these. I don't need you to make a graph that goes to 16, but just keep in mind what's happening there. The other thing that they asked me about is the y-intercept, which is really nice if your graph has the y-intercept on it, but this one does not. So we have to think about algebraically, how can we find a y-intercept? So maybe think about what is the definition of a y-intercept? Or the graph crosses the y-axis. So what do we know about every point on the y-axis? What does x equal on the y-axis? 0. So when it asks you to find the y-intercept, if you don't know what the y-intercept is, like this one, I don't know what the y-intercept is. All you have to do is plug in 0 for x and solve that problem, and that's going to give you your y-intercept. Your y-intercept is when x equals 0, what does y equal? So on here, all we have to do is plug in 0 for x. And sometimes people get really confused by that because we get so used to slope-intercept form that we should be able to tell the y-intercept by looking at the equation, but that's not true for all equations. So exponents first, so -3 to the third is -27, and -27 times 2 is -54. So my y-intercept would be -54, which I definitely don't want to make my graph go to that. I want to be able to find the y-intercept. Some of your homework today is matching up graphs with equations, and the y-intercept is helpful on that. Like if you look at your y-intercept on those graphs, that's going to help you pick out the right one, and a lot of times you don't have to do much else. Okay? 2 questions on your homework like that. We also want to talk about how to tell what the end of a polynomial function looks like. We call that end behavior, and we do this thing called the leading coefficient test. So I'll let you write that down, and then we'll talk about it. And you'll probably remember this once we start writing it. It'll just take a minute to jog your memory about how you can tell whether it's the end of the graph goes up or goes down, opposite directions. here. I didn't write it as ugly as I made it before, but notice this is just our polynomial function. X to the n is your degree, a sub n is your leading coefficient, and then I just wrote the dot, 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 like where we go all the way down. Made it not as scary as before. But you can tell how your graph's going to end. We call that end behavior by looking at the degree of the polynomial and looking at the leading coefficient. So if your degree is odd, so if the biggest exponent is odd, your graph will always go in opposite directions. Think about x cubed. X cubed, one arrow goes up, one arrow goes down. That works for every odd function. If the leading coefficient is positive, think about x cubed. The positive side goes up, the negative side goes down, right? That's what x cubed looks like. Every odd function that has a leading coefficient is positive, the end arrows look like that, and the middle can be kind of crazy. So how we write that is we say, as x goes to infinity, as x gets bigger, what happens to f of x? Well, as x gets bigger, y gets bigger, so we say f of x goes to infinity. And then we say as x goes to negative infinity, that means on the left side of my graph, as x gets smaller, think about x cubed, y gets smaller. So the in behavior, they go in opposite directions. If your leading coefficient is negative, think about the transformations. A negative flips your graph over the x-axis. So if your leading coefficient is negative, it's going to switch, right? So now the left side of your graph is going to go up, and the right side of your graph is going to go down. But how we write it is we say, as x goes to infinity, f of x is going to negative infinity. And as x goes to negative infinity, f of x is flipped, and now it's going to positive infinity. So you need to know that odd degree polynomials, arrows go in opposite directions, and you got to know which one it is. On your homework today, on your test that we'll have, there will be questions that say, describe the end behavior. These arrows are lovely, but that's not acceptable for describing the end behavior. You got to write it out like this. Remember doing this last year now? Still making your infinity signs, two circles next to each other? I feel like I can't undo this damage that Mr. McClure's done to you. You're going to always make two circles next to each other. So odd, I always think of x cubed. We can also say the same thing about even functions. And even functions, think about x squared, and you'll always remember this. If your degree is even, your arrows are always going to go in the same direction. And if it's positive, they go up. If they're negative, they go down. So if n is even and your leading coefficient is positive, both arrows should end up. And we can just say as x goes to infinity, f of x also goes to infinity. And as x goes to negative infinity, f of x also goes to infinity, because they both point up like x squared. And if you notice, every time it's the same. As x goes to infinity, f of x goes to something. All that changes each time are those end things. So it's just very repetitive over and over again. And again, think about what a negative does to your parabola. A negative flips it over the x-axis, which means if it's even degree and your leading coefficient is negative, both arrows will point down. So we can say as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to negative infinity. In second hour today, they said, do we have to memorize this for the test? Yes, you have to know this. You will not get a cheat sheet to know this. So there will be direct questions asking you to write the end behavior, but when we graph these, this is helpful when you're graphing because you know how the arrows are supposed to end. So that's why it's a nice thing to know. And if you just think about x cubed, x squared, and know that a negative flips it over, it's not really that much to memorize. Okay? We're almost done. We got like one more thing to write, and then we can do examples. Are we looking at having a test next week? Just throwing that out there. Thinking about it. two of them. And here. And two others are outside. Alright. Normally, like, half my pre-calc class is not, but with this college algebra this year, like, I don't have as many seniors taking pre-calculus. It's very, small amount. Are you okay with this? Can I go? The last big thing today is talking about whether your zero touches or crosses the x-axis, which I don't think is something that you learn in Algebra 2. The whole arrows is something we do in Algebra 2. But this, talking about whether your zero touches or crosses, I think is a pre-cal thing. So, it says, if you have f of x equals x to the n, where n is an integer, that just means it's polynomial. Nothing crazy going on, no negative exponents, none of that's going to happen. But if you have your zero there, and if that power is even, then when you graph that zero, it's only going to touch the x-axis and not actually cross it at that zero. Again, think about x squared. Y equals x squared. It has a zero at 0, but it just comes down and touches it, right? Like I could make it like this. That sort of touches it. Right? It doesn't actually cross the x-axis. But if you have an odd degree of a zero, then it's actually going to cross the x-axis, which is what most of the time happens. Like 1 is an odd number, and that's what the power is most of the time. But think about x cubed. X cubed also has a 0 at 0, but because it's odd, it actually crosses over the x-axis. And so you can tell in behavior of a graph by just looking at the equation. If you know the zeros, you can tell whether each zero touches or crosses by just looking at the graph. By just looking at the equation. And so you get a pretty good idea of that graph without actually making a big XY chart. So part of your homework today is going to be describing the end behavior and also finding the zeros. But the good thing is they give you nice factored ones today. So let me kind of show you what your homework looks like for most of it. Some of your homework just says describe the end behavior, but I want to do this part. Find all the zeros and describe the end behavior. Makes me wonder if the book spells zeros with O. Yeah, the book just says Z-E-R-O-S like me. And it doesn't say to tell whether each zero touches or crosses, but I'm going to do that as we go through this, just to kind of show you how this is helpful. But the good news for us today is we don't have to do PRZs and synthetic division. That's not till section 2.4. They're factored for us, which means to find the zeros of this, what do? Yeah, these are factored already, so you just set each one equal to 0, which means probably you're not even going to show that work. You're just going to say, well, if this is equal to 0, that means I have a 0 at 1. If this is 0, that means I have a 0 at -2. And if I set that equal to 0, I have a 0 at -3. That's good fun, right? And because each of these zeros, although it's not written like this, x to the n, but each one of these, you see how this is all to the first power, each one of those individually? Because those are all to the first power, we could say they're all odd, which means that all of these zeros would cross over the x-axis. All right, if this would have been x plus 3 squared on the outside, that would have made it just touch instead of cross. And so that's kind of what that has to do with the zeros. The end behavior you got to think about a little bit, because the end behavior you have to figure out the degree and you have to figure out the leading coefficient, which means you have to think about what you would get if you multiplied all this out. You don't need to multiply it all out because you just need the leading term. So I just think about if I take all the biggest terms from each one, if I took x times x times x, what would I get in this? X cubed, right? So if that's x cubed, I can use that to find my end behavior. And x cubed is odd, which means your arrows should go in opposite directions. And because that's a positive number in front of that, you would say, as x goes to infinity, f of x goes to something. As x goes to negative infinity, f of x goes to something. Every time, that's how you set up your end behavior. And then you have to make sure you know the answer to this. If it's odd, they go in opposite directions. And to me, I always think positive goes with positive, negative goes with negative. So positive goes with positive, negative goes with negative. Maybe my negative. So zeros in behavior. So let's try this one. You give a head start on that one. See if you can do the zeros and see if you can do the in behavior. The zero part hopefully isn't that bad. Just set each one equal to 0. So on this one, I would subtract 1 and divide by 2, and I would get x equals negative 1/2. And on this one, I would just add 4, and I would get x equals 4. These are both odd zeros again, because this is a 3, and that's really just the first power, which means they would both cross if we were looking at that part. What about the degree of this one? And you got to be careful on this one. It's not just 2x times x, right? Because you'd have to think about that this is x minus 4 3 times. So that would be x times x times x, which is x cubed, times 2x. So I just think about taking the biggest x from each one, which means 2x to the 4th would be our leading term on that one. Do you agree with me on that? That's an even degree, so that means the arrows go in the same direction. And because it's positive, then they both go up. So the answer should be, that's a lovely infinity sign. Both going to positive infinity. Don't go to sleep now, Bryce. You're doing so good. All right, I got one more. Handwritten and everything. Okay, one more, please. One more after this, too. How many examples do you have left? We have 2 more examples, counting this. I thought I'd throw in a tricky one here. There's an update to my smartboard today, like the smartboard software, and now every time I write, it like changes. I don't. It's probably not even noticeable to you, but I notice it as I'm writing. Like it like adjusts the ink, and it's driving me crazy because I don't know why it's doing it. Hopefully the zeros aren't so bad, right? This one would just be add 4 divided by 3. But again, just to throw this out here, because that's all squared, and we'll talk about this more tomorrow, but that means if we graph that 0, it would just touch the x-axis at 4/3. It wouldn't actually cross. As opposed to this one, it's odd. It would cross, and where would it cross at? What would the 0 be? Positive 2, because you could subtract 2 over, but then you have to divide by negative. So it would be 2. What about the leading term on this one? What would be the leading term if I just worked out 3x minus 4 squared? But it would be, this one would be 3x squared, right? You have to square this first, so that would be 3x times 3x, which would be 9x squared. That's just this part, right? And what am I going to multiply it over here? By the 2 or by the negative x? Okay, you have to take the biggest x from each one. So you would have to multiply that by negative x. So our leading term would be negative 9x cubed. So just watch out on that. A little tricky sometimes. It is odd, so opposite directions, and it is negative because of that negative x, which means odd goes in opposite directions, and negative means they flip. So now the positive side goes down, and the negative side goes up. Some of your homework is just in behavior, like not foiled out like this, and it's actually much easier than this. That's why I thought I would do the hard ones. And I'll show you the next one, but we're not really going to do it. We're just going to look at it for fun, and then we're going to do one more. Unless you really want to do it, we can. So like this is also on your homework, but it's already worked out for you. So if I asked you to find the end behavior of this, do you agree we would just look at the biggest exponent? It would be even, positive, and we'd say they both go up. You okay with me not working that out? I feel like that one were harder. So let's do this one, which I think is now number 5 with all my changing around. The last thing on your homework today is directions like this, and it says find the zeros of the function algebraically, which for us right now means it should be able to factor. Right, this goes hand in hand with your quiz tomorrow. We have questions like this on your quiz tomorrow. In college algebra. I can't tell you that. Not always, but pretty good at hint. Because if you have a worksheet, a good hint for having homework quiz if you haven't caught on to that. Well, sometimes I like to go in and I'm not worksheet quizzes. You might say, how do I factor this? Because it's not x squared, but what could you actually factor out of this first? Yeah, we could factor out of 5x, and we would be left with x squared minus x minus 2. And so today they work out really nicely that you should be able to factor all of these. And 2 is a prime number, so it has to factor into 2 times 1. And just make sure you get your signs right. To get a negative in the middle, you need a negative 2 and a positive 1. And just like what we did on the ones that were already factored for us, is now you just break it up and set each one equal to 0. But don't forget to set that front part equal to 0 also, because it does have an x in it. So you do actually get 3 zeros on this one. Because if you set this equal to 0, you get x equals 0, you get x equals 2, and you get x equals negative 1. And that's it. That's all you do on that one. So in behavior and finding the zeros tells us a lot about a graph. All right, so your homework, I want to make sure we talk about the directions of this because we have to ignore some of the directions sometimes. Are you okay with that? Fine. You good? So this is homework 2-3 day 1. The assignment is 3, 6, and 18 through 36 multiples of 3. On number 24, just do the end behavior. It asks you to find the zeros, but they want you to do the zeros with a calculator. That's what we're going to look at on Wednesday. We're going to spend time working with our graphing calculators. So 24, just do the end behavior, and you're only graphing 3 and 6 if If the other ones say graph in your viewing window, again, they're expecting that you have a graphing calculator, so you're not expected to graph anything but 3 and 6 on your homework today.